Dear students, in this lecture we will learn about the eigenvalues and eigenvectors. This topic is a new topic and you didn't study this topic before in your classes, so try to understand the idea of these two. That is not too much difficult, but a bit tricky. That is the definition. For example, for a square matrix, we have got a square matrix of order n by n. N by n, we have got a square matrix. So remember that whenever you are talking about eigenvalues or eigenvectors, so we will be deal there with square matrices. So we have got a square matrix A, and whose order is n by n. It means that this matrix has n rows and n columns, and let's say we have a vector x belongs to Rn. It means that this vector has n components, x1, x2, x3 up to xn. So whatever the order of A, we will take the vector with the same length. If that is 2 by 2, so x will belong to R square. If that is 3 by 3, so x will belong to R cube, and so on. So we say that A is a matrix whose order is n by n, and we have taken a vector x belongs to Rn. Then this vector x is said to be the eigenvector of this matrix A if we multiply x with A and get lambda times x, lambda times that x. Lambda is actually a scalar number which may be negative, may be positive, may be zero, but scalar is actually a number which is a non-zero number. Anyways, ax is equal to lambda times the same x. Then we say that this x is the eigenvector of this matrix A, and this lambda, which is actually a scalar number, is called the eigenvalue of this matrix A. X is the eigenvector of A, and lambda is the eigenvalue of A. That is the definition. What is the geometrical meaning of lambda x? Lambda x, we are going to multiply a scalar number with the vector. So if that scalar lies between 0 and 1, 0 and 1, 1 by 2, 1 by 3, lambda is actually less than 1. So if you see here, this is the length of the original x, and whenever you multiply lambda with that x, and lambda is less than 1, so it will reduce the size of this full vector x. Now that is actually lambda x, because lambda lies between 0 and 1. Whenever lambda lies between 0 and 1, it will reduce the size of the original matrix. And whenever x is greater than or equal to 1, it means that x is greater than 1. So whenever lambda is greater than 1, then it will increase the size of the original vector. That is the length of the original vector x. And whenever you multiply lambda, which is actually greater than 1, greater than 1 means, for example, that is 2, 3, 4, and so on and so on. So whenever you multiply 2 with this x, so that will become 2x. It means that the length of this original vector will increase 2 times. And whenever you multiply 3 with x, so the length of this vector x will be increased 3 times. Anyways, when lambda is greater than 1, so that will increase the size of the original vector, and the direction is the same. In these two cases, we see that lambda is positive number. Lambda is positive, not negative. So the direction of the original vector will not be changed. That is direction of lambda x, and that is the direction of the original x. Similarly, if this is the direction of x, then the same direction for vector lambda x. And whenever lambda is negative, we see here, whenever lambda lies between -1 and 0, -1 and 0, that is lambda is greater than -1. So in the same sense, whenever this lambda reduces the size of the original x, the same will be repeated here, that whenever lambda lies between -1 and 0, it will reduce the size of this original x, but direction will be changed, that is lambda x. And we see that this length is less than the length of the original x vector. So whenever lambda is negative, it will change the direction of the original vector, and whenever lambda lies between -1 and 0, the length will also be lessen. And in this sense, whenever lambda is less than -1, lambda less than -1 means -2, -3, -4, and so on and so on. So it will increase whenever we multiply lambda with the original vector x, that is the original vector x, and lambda is multiplied with this vector x, so it increases the size of the original vector, and the direction is opposite because lambda is negative. So that is the geometrical meaning of this lambda, that what is the effect of this eigenvalue on the original vector x. Now the question is, how could we find the eigenvalues for a square matrix? Eigenvalues mean the values of lambda. How could we find the values of lambda for a square matrix? So these are the steps. As lambda is the eigenvalue, so from the previous slide we can write ax is equal to lambda x, that is from the previous slide. Now shifting lambda x toward that side, so that will become minus lambda x is equal to 0, and taking x common in these two terms, so that will become just like that, because these are vectors, and x is actually, you can say that that is a vector which is in the form of a matrix. A is also a matrix, so whenever we take x common from these two, so identity matrix will be left here instead of this x, so lambda into I is equal to 0. Or we may revert these two. If we take minus sign common from these two terms and multiplying both sides by a negative sign, we will get this equation, lambda I minus a into x is equal to 0. Whatever the equation is, either this equation or that equation, both have the same meaning. So in your book this equation is used, so that's why I have written this equation. So lambda I minus a into x is equal to 0 is obtained from the original equation, from the definition, lambda I minus a into x is equal to 0. To find the value of this lambda, which is actually the eigenvalue of the matrix A in this case, we take the characteristic equation. What is the characteristic equation? That is actually the difference of these two along with determinant, lambda I minus a. Determinant of lambda I minus a is equal to 0 is called the characteristic equation for this square matrix A. I repeat, ignoring this x and taking the determinant of lambda I minus a and equate it to 0. Determinant of lambda I minus a is equal to 0 is called the characteristic equation for this matrix A. This characteristic equation is used to find the value of lambda or to find the eigenvalues, because lambda is actually the eigenvalue. This equation when we expand this determinant by any row or by any column, we get a polynomial in lambda, so that's why this equation, which is the characteristic equation, this equation is also called characteristic polynomial, characteristic equation or characteristic polynomial. That is question number 1 from page number 9. Find the characteristic equation of the following matrices. That is a matrix A. We have denoted this matrix by A. You can denote this matrix by B as well. Whenever you denote this matrix by B, we will write here B, and whenever you denote this matrix by C, we will write here C instead of A. So anyways, we are going to find the characteristic equation of this matrix, and we see that this matrix is a square matrix. That is the characteristic equation actually. This is the characteristic equation. So the characteristic equation is determinant of lambda I minus A is equal to 0. Now putting the values of A, that is matrix A, and replace identity matrix. We see here that A is 2 by 2 matrix, so we will take this identity matrix 2 by 2, 1 0 0 1. So that will become determinant of lambda into I minus this matrix A. Now first of all, multiply this lambda inside with all these 4 numbers, so that will become lambda, that will become 0, that will become 0, that will become lambda. So determinant of this matrix minus that. Now that is the difference of these two matrices. What will the difference? First minus first, second minus second, third minus third, fourth minus fourth. So determinant of lambda minus 3, 0 minus 0, 0 minus 8, lambda minus into plus, so lambda plus 1. So determinant of this matrix is equal to 0. Now how could we find the determinant of this matrix? That is AD minus BC. First of all, we write this matrix in the standard form. I mean 0 minus 0 is 0, 0 minus 8 is minus 8. Now determinant of this matrix is this and to that minus this and to that. So that is lambda plus 1 into lambda minus 3 minus 8 into 0 is 0 is equal to 0. And multiplying these two, lambda square minus 3 lambda plus lambda minus 3. Minus 3 lambda plus lambda is minus 2 lambda. So lambda square minus 2 lambda minus 3 is equal to 0. This is the characteristic equation for this matrix A. So that is the whole story, that how could we find the characteristic equation for a square matrix. That is, this is the characteristic equation. Determinant of lambda I minus A is equal to 0. So that is your question number 1. And now question number 2, find the eigenvalues of the matrices in exercise 1. The same exercise, the same question. I mean question number 1. This is the matrix A. We are going to find the eigenvalues of this matrix. So how could we find the eigenvalues of this matrix? First of all, eigenvalues means the values of lambda. First of all, we find the characteristic equation, and after that we will solve that characteristic equation to find the value of lambda. So that is the topic which is already studied in the previous topic slide. So So the characteristic equation is determinant of lambda I minus a is equal to 0. That is the same in the previous slide. Replace I by this, a by its own value. Now multiplying lambda inside, subtracting these two matrices, simplifying inside, and taking the determinant of this matrix, AD, this into that minus this into that, lambda plus 1 into lambda minus 3 minus 0 into minus 8 is 0. And now multiplying these two, we'll get this equation, and this equation is actually quadratic equation. Solving this equation by factorization, 3 ones are 3. So how could we factorize 3 ones are 3? So we write minus 2 lambda is minus 3 lambda plus lambda minus 3. Now taking lambda common from these two, so that is lambda minus 3, and taking plus 1 common from here, we'll get this equation. Lambda minus 3 is common in these two, so lambda minus 3 into lambda plus 1, and it means that either lambda minus 3 is 0 or lambda plus 1 is 0. So from these two equations we obtained lambda is equal to 3 and lambda is equal to minus 1. So the eigenvalues are lambda is equal to minus 1 and 3. So that is the criteria to find the eigenvalues of a square matrix. Now in this slide and the previous slides, we have considered 2 by 2 matrices, and in this slide we will be dealt with the 3 by 3 matrices. How could we find the characteristic equation of a matrix of order 3? So the same story is here. The characteristic equation is the same, determinant of lambda I minus a is equal to 0. Now we see here that A is actually 3 by 3 matrix, so we will take identity 3 by 3 as well, 3 rows and 3 columns. Now multiplying lambda inside with 1, 1 and 1, because all the entries are 0 except these, so lambda, lambda, lambda. Just look at that. Now subtracting these two, lambda minus 4, 0 minus 0, 0 minus 1, and so on, so on, so on. Now simplifying this, 0 minus 0 is 0, 0 minus 1 is minus 1, 0 plus 2 is 2, 0 minus 0 is 0, and so on. Now determinant of this 3 by 3 matrix, what will be the determinant of this? We need to expand by row number 1. You can expand it by column number 1 as well. You can expand it by column number 2 as well. Anyways, I have expanded this determinant by row number 1. So how could we expand it? Lambda minus 4 times excluding lambda minus 4, that column and that row, we are left with this determinant. And now plus 0, that is 0, so there is no need to write the cofactor with this 0, so ignore this 0 and take this minus 1, so minus 1. Now exclude that row which contains minus 1 and that column which contains minus 1. So ignoring these two, we are left with 2 lambda minus 1 2 0 is equal to 0. And determinant of this 2 by 2 matrix is this into that, minus lambda minus 1 into lambda minus 1 is lambda minus 1 whole square, minus 0 minus 0 is 0, minus 1, 0 into 2 is 0, minus 2 into lambda minus 1 is equal to 0. Now simplifying this equation, lambda minus 4 into lambda minus 1 whole square, minus minus plus, 1 2s are 2, lambda minus 1. And we see that lambda minus 1 is common in these two terms, so taking lambda minus 1 common, So we are left with the lambda minus 4 here and lambda minus 1 here, and we are left with 2 here. Now multiplying these two, lambda square minus lambda minus 4 lambda plus 4, these 4 terms plus 2, and simplifying, lambda square minus lambda minus 4 lambda is minus 5 lambda plus 4 plus 2 is 6. So that is actually the characteristic equation. You can simplify this equation as well by multiplying lambda inside and minus 1 inside, but there is no need. This is actually the characteristic equation for this matrix A. So this is how we find the characteristic equation of 3 by 3 matrix. The idea is the same, but we need to expand the determinant by a row, a specific row or a specific column. Anyways, that is the characteristic equation of this matrix. Now in the coming slide, we are going to find the eigenvalues of the matrices in the same question 4. That is the same matrix, but for this matrix we are going to find the eigenvalues. How could we find the eigenvalues? That is the same topic as discussed before, that we will take the characteristic equation, which is determinant of lambda I minus a is equal to 0. Now replacing I and replacing a here, I is 3 by 3 identity matrix and a is this matrix. That is the same story as discussed in the previous slide, that multiply lambda inside and subtracting these two matrices, and then find the determinant of this matrix by expanding by row number 1 and simplifying to get this equation as in the previous slide. That is the same story as in the previous slide. Now this is the characteristic equation, but we need to find the eigenvalues. Eigenvalues means the values of lambda. So for the values of lambda we need to solve this equation, factorizing this equation. That is the these are the factors: minus 2 minus 3, 2 3s are 6, and minus 2 minus 3 is minus 5. So now taking lambda common from these two and minus 3 common from these two, and then lambda minus 2 common from these two to get these three factors. Now from here, either this equal to 0 or that equal to 0 or that equal to 0. So we are having lambda equal to 1, 2 and 3. So these lambdas are the eigenvalues of this matrix A. That is a very simple topic. So this is how to find the eigenvalues of a 3 by 3 matrix. In this slide, how could we find the eigenvalues of upper, lower and diagonal matrices? What is upper matrix, upper triangular matrix, or lower triangular matrix, or diagonal matrix? Let us take examples here. That is a square matrix in which this is the main diagonal of this square matrix. Below this main diagonal there is 0 and above is non-zero, so that is upper triangular. And whenever above main diagonal is 0 and below is not 0, that is lower triangular matrix. And if above and below the main diagonal there are zeros, both are zeros, then we say that this is diagonal matrix. So what is the eigenvalues of these kind of matrices? So I have discussed here that taking the characteristic equation of this matrix, replacing I, because A is 2 by 2, so that's why we have replaced I by 2 by 2 matrix and A by its own value. Multiplying this lambda inside, subtracting these two matrices, and determinant of this matrix is this into that minus this into that is equal to 0, and we obtained the eigenvalues 2 and 4. we see that this 2 and this 4 is actually the main diagonal of this matrix. So whenever you are given upper triangular matrix, then directly we can say that the eigenvalues of this matrix are 2 and 4. Similarly, if a matrix is lower triangular, so repeating the same story, we obtain here 2 and 5 as eigenvalues, and 2 and 5 is actually the main diagonal of this lower triangular matrix. So whenever a matrix is lower triangular, then its eigenvalues are the entries of diagonal 2 and 5. Similarly, if a matrix is diagonal, repeating the same story, we get eigenvalues 3 and 7, and that 3 and 7 is actually the main diagonal of this C. So whenever upper triangular matrix, lower triangular matrix or diagonal matrices are given, then the eigenvalues are the numbers and the main diagonal. That is question number 10, page number 11. It says that by inspection find the eigenvalues of the following matrices. That is a matrix A minus 1, 6, 0 and 5. We see that this matrix is upper triangular matrix because below this main diagonal there is 0 and upper is not 0. Anyways, so its eigenvalues are minus 1 and 5. S is upper triangular matrix, so its eigenvalues are the entries in the main diagonal, that is lambda equal to minus 1 and lambda equal to 5. Similarly, that is B. We see here that this matrix A is lower triangular matrix because above this main diagonal all the entries are 0 and below are not 0. So the eigenvalues of this matrix are 3, 7 and 1. That is written here. As lower triangular matrix, so its eigenvalues are 3, 7 and 1. So that's how we find the eigenvalues of triangular and diagonal matrices.